All righty. Hey, everybody. Happy Bayesian machine learning evening. We've got lots of good stuff to cover. So I'm going to jump in. I'm going to start with a little bit of announcements, which I sent an email about, so you might have seen them, but I want to make sure we check in. Oh, I just uploaded the copy of the slides to our site. So if you want these slides, they're in the file section on our Canvas. I got myself a pen so I can write on these. So today we're going to talk about conjugate priors. We're going to kind of pick up from last time a little bit, but we're going to talk about conjugate priors would be our main topic. But here's the big announcement. I deleted all the quizzes from modules 1 and 2. So I don't know how many people ran into, we had different problems with those. We updated some things in Canvas, and the quizzes I wrote for the class previously were not compatible with the updates. How's my audio? Is it okay? Is it good? Okay. Last time I think I had two things using my audio, so but the microphone's good when it works. Okay, so what I did is I just deleted all those. I don't want you to waste your time on things that may or may not give you the correct answer, that may or may not allow you to submit the right answer. There were all sorts of problems. So I get rid of those. All your grades will be normalized. Like those will just be removed and everything will be normalized. If there's anything particular we have to do for those. But I really, what I want you to do is be able to focus your time on homework 1 now instead of trying to make those up, right? Does that seem good? I think it should be a net benefit, a little bit less work for you and pressure to get those in, and you can focus on homework 1. So we're going to talk about that today. So here's what we're going to talk about today. First, we're going to talk about I'll give a little brief discussion about additional materials. I guess this is in slightly wrong order. We're going to talk about priors. We started talking about those a little bit last time. Bayes' theorem. Really, the general idea of computing priors is going to be a big thing today, and then we'll go through a specific example. We're going to talk about some Python code. Okay, so here's the additional materials. Now, I'm really big on this. When I was in grad school, every time I took a class, I had the textbook for the class, and I had like 4 other books on the subject, and I would read those and try to get as much different information. You have a nice advantage today, and particularly being in data science, that there's a lot of videos. And I was born in the Stone Age. I went to grad school in the Stone Age before Wikipedia existed. So I couldn't look things up there, but you have lots of videos on YouTube, you have Wikipedia, and there's a lot of really good data science blogs. So I have these. They're going to be super helpful for you in the class. So I put them here, but also it's good habits to get used to these, right? So this Towards Data Science blog site, I did a job interview for a data science job at one point, and one of the questions, I thought this is a great question. So if you ever interviewing people, remember this, and if you ever go into an interview, remember it so you can be ready to answer. They said, what's your favorite blog site to read data science blogs from? Because it's a great way to get little snippets of information that's like usable and short and bite-sized and digestible, but hopefully still rigorous. So Towards Data Science was my answer, and it's still my answer today. So they've got 2 really good, and they're kind of this title, A Gentle Introduction to Conjugate Priors, and Conjugate Priors Explained. And you look here, right, it's our old friend Bayes' theorem, and they're breaking out the different pieces. So it's really friendly, readable things. This is the Oxford online class, and this is the display of how it looks. They're going through Bayesian statistics, not so much machine learning, but Bayesian statistics. It's a little different perspective, really complements the way we discuss things nicely. And really a lot of the homework problems, if you watch this course, they'll do problems which are the same as the homework problems that we'd be doing. So if you're like, oh, I feel a little insecure because I didn't get the chance to go through those and see the answers, those types of problems are covered in that video, right? And then we're going to use this a lot, but I wanted to highlight it here. There's the conjugate prior page on Wikipedia, and so we'll see that. In fact, I added these to page 2, module 2.1, And here's all this additional material here, and then here's the web material. So make sure you read all those. Like I have no way of checking that you read them. I don't know if there's material specifically, like if you don't read them, you'd get a question wrong, but assume the required reading, right? Does that make sense? Because I care about you and I want you to learn, and that's the best way to learn those. Okay, so let's jump into material. Oh, I spent a couple of days last week trying to fix all the quizzes because my goal at first just one more update. And my goal was to fix them and then walk through them in office hours. But I burned all my time that I have that's not nailed down for something trying to fix those, and it turned out they were unfixable. So we wound up without office hours last week. So I apologize for that. We'll have office hours this week on Friday at 1 o'clock, and we'll be working on homework 1. So we're going to start looking at homework 1 probably at the end of class today, and then we'll start going to it. Yes, Dima.
Yes, hi, Professor. About the quizzes, I was working on the quizzes for module 1 today, and suddenly they disappeared.
Yep.
Okay.
Yeah, that's because I deleted them.
Okay.
They were causing people more problems and confusion trying to do them. Then there were some of them that would give the wrong feedback around what's correct. There were some of them where you would try to type a number in and it would like round it to something weird. And there were things that should have been a number answer that you put in that it expected, and it was set up to be accepting like a text answer. And those are just the errors that you see. Like there were lots of errors under the hood that,
no quizzes in this course?
Yeah, so we're gonna have one quiz in like chapter 12 or something. But we'll talk about that when we get to it, kind of a review thing.
Okay. We're just focusing on homeworks now, right?
Yep. Yeah. Yep. And all the material that was in the quizzes is covered in that Oxford YouTube video. That's very much the flavor of the quizzes is here's a little problem. How do you put the numbers in to get the answer? Right.
And same with the proposal that was due today, the proposal, what we would like to do for the final project.
Yeah, for the proposal that's due today, write me something, just an idea about a final project. There's almost no wrong answer.
In Teams?
So, yeah, Teams is fine. Or is there a spot to submit it there?
Yeah, let's maybe start a new channel there. Well, not a channel, but just like sub-rubric.
Okay.
Oh, thank you very much.
Let me write myself a post-it note.
I think there's an assignment in Canvas where we would submit the like paragraph. Like if you could.
Okay, good. Yeah, there should.
There's an assignment there.
Yeah,
there is an assignment there, but I'm just wondering, I'm just a little confused, like how much detail we have to go into. Just some more direction would be nice.
Yep. All I want now is just kind of some idea. Slightly more information than when you gave an introduction and said, hey, here's something I'm interested in doing. It just kind of let me know where you're at. If you have a data set, then that's great. If you have a problem that you're thinking of, that's great. If you're on a team with a couple of people on a capstone group, then just let me know who's in your group and what the problem is, that kind of a thing.
Okay, cool.
We'll do a more rigorous proposal later on. This is kind of just to,
Did we have assembled a team already?
No. So if you have a team in a capstone you're working with, then you can let me know. This just to start thinking about a project early on.
Okay.
That's all. Right. And I will tell you at the end of the class, the project is going to be use something we learned in this class, use a Bayesian method for machine learning on some problem. Right. So it won't be, the goal doesn't have to be answer the solution that the person, like your customer, would be looking for. It's use a Bayesian method to get some insight. Right. So, but we'll talk about that later on when we get to it. I like that scope for that final project because the goal isn't get the most accurate thing possible, but it's get some insight through a Bayesian method.
Okay.
But yeah, we'll get to it. Yeah.
That's,
Just, sorry,
um,
one more question about the project. Is it individual or group? Just to make sure I'm understanding correctly.
Normally it's groups, and I like groups, but sometimes individual, if you want to do it individual, that's a possibility too. So if you have any thoughts on that, put that in your proposal spot. I like groups. I had to occasionally use a student who's working somewhere and has relevant data from their job and is like, hey,
Gotcha.
this really, that kind of thing.
Okay, great.
Yeah, good, thanks.
it's assignment 116, project proposal. I cannot see it in the modules. So when I'm going through the modules, it's not there, but I can still see it under assignments. So if I click on assignments, this assignment is still there. I cannot complete it as a regular assignment, but I can add a comment. So that's a text field that I can actually type into. And so I guess the submission will be the comment. Thomas.
Yeah, if there's a spot for a comment, however, it has to put something in there. I'm going to check it after we're done here, but I want to make sure we get through the material here. So I got my posting note. I'll make sure I check it. I'll send an email after class.
Sorry to waste time on this. Sorry.
No, that's okay. It's good. It's good. Okay, so we're going to talk, and this is something we talked about, so we're connecting with last time, something called conditioning, which is really how do we deal with this? How do we get the piece that's going to go in the bottom in Bayes' theorem, right? And so really with Bayes' theorem, I think this thing often happens. You're like, do a little bit of work and you're like, oh, that's obvious. You go away for a day and you come back and you're like, what the heck is that thing? Right. So it kind of has that sense. So you walk away. That's why I want these different sources that give a little different perspective. And we're going to get into doing computations, but for the moment, and if you don't remember it, that like what all the pieces are explicitly, we're just going to talk about this piece here for the moment. And I want you to familiarize, connect that with the word conditioning. So Professor Brown, who does the lectures, uses the word conditioning to talk about that. So just to remind us, theta is the parameter, and we're going to do a concrete example in a second. X is always our data. And the goal is, in Bayesian world, we've done some experiment. We picked 10 flowers and measured their height. Or we watched a road, we counted the number of car accidents on that road in a month. Or I flipped a coin 21 times, 50 times, I got 21 heads. We're going to stick with that as a concrete example for a while, the coin problem. It's a really flexible framework, but just to take something really concrete, we'll do that. So the data is how many heads I got from flipping the coin, right? And that's fixed, right? I did the experiment, I got the outcome, that's fixed. The part that's unknown is what's the probability of getting heads on that coin, or what's the probability of my team winning a tournament, right? If I have a strategy for a chess match and I'm going to play grandmasters, what's the probability that that strategy is going to win, right? That's the kind of thing that that we try to estimate, right? And so that's our parameter. So let me go back to the coin, probability of getting heads, because it's just one example. So that would be P. Okay, but this bottom piece, it's the probability of getting the data, but we want to compute that probability irrespective of what the parameter is. So to do that, we use this formula. This is the probability of getting like 21 heads out of 50 flips, but we don't know theta. So what we do is we do the probability for each value of theta times the probability of getting that outcome given that probability, and we sum it over all possible values for theta. Now, does anybody remember what this is called? We have a name for this probability, probability distribution computed this way.
I think it was called total probability.
Total probability is a good name. And I think that's correct. I think it's called that. This is the marginal probability, right? Where you have a probability that depends on two variables, in this case, X and theta, and you want to just get rid of one of those variables and do probability of just the x. And so you take the probability, you sum it over all the different possible values for theta. When we did it as partial probability, we did it like in a little table, and it was super easy, and everybody was probably like, yeah, that's obvious. So I really just kind of want to emphasize it's a pretty simple thing. And another way to derive this, so we could think about this as a proof. So this is, or of proof of this formula, which is sometimes called conditioning, and it comes from marginal probability. And so here's the proof. So we start with the definition of marginal probability, which is that, right? You want this probability, and you have two variables, and you want to get rid of one of them. You fix your variable you care about, which is x, and you sum over all possible values for the other variable. Then we insert the definition of a conditional probability into this. And so this is the definition of conventional probability. We just modify it a little bit, right? We multiply both sides by this to get this. We take this piece and substitute it in for that. And that leaves us with this. Okay, that's kind of the formalism around where we get this from. Where this what that happens to be is just a term that makes our posterior probability distribution sum to 1. And we're going to see that in a minute. So let's do some computations. I always find things make more sense when I do them as a computation. Okay, so let's fix our simple example. So we get a coin, we're going to flip it 50 times, and we'll get 21 heads. And the question is, what's P? Now, okay, so let's take a little more careful look at this. If I flipped the coin 50 times and got 21 heads, what do you think the probability of heads would be? Just knowing that. So I see, so this is a funny thing. I see 50% or 0.5, which are really good answers. If I never tested the coin, that's probably what I would get. But if I got 21 heads out of 50 flips, that would be 42 out of 100, or a probability of 0.42 as my probability of getting heads. So if I know nothing about coins, I would say, the probability of getting heads is 0.42. If I know nothing about data, I say my probability of getting heads is 0.5. This is the beauty of Bayesian machine learning, that allows us to put those two pieces of information together to get something rigorous, right? So if you came out and you said, oh, I think it's 0.42, right? The next question that we want to ask is, okay, how confident are you that it's 0.42? Or maybe you thought the answer was 0.5, and the question is, how confident is are you 95% sure that it's within 0.05 of that value that you think it is? Like, so these are all the pieces that Bayesian methods allow us. So do you think I talked long enough to get 50 flips by Fred here? I don't know. Okay. Actually, Barney's flipping it. Anyway, do you guys, are you familiar with this cartoon, the Flintstones?
Yeah.
Somewhat. Okay, this is like it's like my childhood. Okay, so let's go back to Bayes' theorem, and instead of being a little abstract with these pieces, we're gonna decide what x is going to be. It's this coin flipping problem. So x is going to correspond to my data, which means I flipped a coin 50 times, I got 21 heads, or k equals 50 and n equals 21, right? The k is the number of flips, n is the number of successes. Theta, I don't know. And theta is going to correspond to p, right? Theta is like a stand-in variable for all our parameters describing whatever we're considering. In this case, it's just one parameter, just p. So what we wanted is a probability distribution that describes our belief about theta, or what the probability is for theta. Okay, so first thing to do to make this more concrete, we said this piece is the likelihood. And the likelihood is what you get when you take the probability mass function or probability density function. In this case, it's a PMF, probability mass function. and you just stick in your values for X and theta into there. And so, so X is these two values, 21 and 50. So N is 50, K is 21, K is 21, and it's 50, K is 21. So it's 50, choose 21 times P to the 21 times 1 minus P to the 29. 29? Yeah. So, okay, so if you gave me a value for P, I could put it in this formula here. And this formula would be the thing that's up here. And I could tell you what the likelihood for that value of P is, right? The place where this is the largest is at P equals 0.42, because 42% of the time we got heads, right? That's, I mean, you could play around with that, or you can just kind of think about what the likelihood means. Okay, so the other thing here, I guess I should mention the theta, which is P, that is coming up right here in these formulas. So when I write this formula in the likelihood in, okay, sometimes I get too many colors, but in this, actually, let's go back to here. When we think about the likelihood, we think about our data as fixed, right? So what's fixed here? And maybe the better question is, in this piece I'm underlining in red, what's the variable? Not too hard, as long as you don't overthink the question, right? In this piece here, P is the variable, right? Right, it's the only letter in there. Everything else we've put a number in because our data is fixed. That's we can put numbers in for the data. P is a variable. We could put lots of different values for P. We could get a likelihood for each of those. And then we could use the other pieces of Bayes' theorem to turn those likelihoods into probabilities. So let's talk about how to do that. Okay, so what we want to do is take this here, which is our likelihood, and we're going to put it, right, to put it into the formulas. We're going to put that formula here. And remember the bottom, this piece, we said that that's the sum over all possible values of P, all possible values of P that we're going to think about or consider. And then you just take the same formula you had here and you put it in there, and then you multiply it by your prior, your P. So let's go ahead and do that. And we're going to do that in this notebook. And this connects with the notebook that we were working with last time. So last time we opened up a notebook in Kaggle, and the notebook was probabilities, likelihoods, and Bayes' theorem. The one we're doing now is part 2. I guess I have to sign in. So I like doing some rigorous, I always like, when I do something in code, I know exactly what all the pieces are, and it helps me to like make things concrete. So I'm going to edit this. And okay, a question I think from Ben. We are looking for the probability that's exactly 21 heads. This is a really great question. It's really getting to the point. Or that it's at least 21 heads, or what probability are we looking at? And so that's what Ben's kind of question asking in the chat. And we're going to answer that in a second. And that's part of how we, like, that's up to us. We haven't defined what values of P we're going to be thinking about. Okay, so I hit the run all button. That way, it'll read all the variables. I don't really care about the top. This part about computing likelihoods we did last time. And then this what's part 3 here. This is where we're going to start today. So here's Bayes' theorem. And so do you see my cursor on the screen if I point to things?
Yep.
Yep. Okay. Good. And so P of theta given X, it's the probability distribution for the parameter theta given an observed outcome X. Or if I think of one particular value for theta, like theta equals 0.42, I could say this is the probability that theta equals 0.42, but there's lots of different values that I could put in there for P or for theta. And the probability distribution will give me a probability for each of those. And we're treating this as the discrete case where we only have a finite number of possible values for theta to put in there. So when we get to this question, if you want to read down to it, it's going to be a little more specific. But let's remind ourselves the pieces. P of theta given X, that's the probability for theta, assuming our data X. P of X given theta, this is the likelihood for the probability distribution, meaning we just use the PMF, probability mass function, we put everything into it for the data, and we're going to wind up with the parameter as our variable. P of theta is our prior probability for theta. We're going to talk more today about what that means. And P of X is the probability of getting X as an outcome if we knew nothing about what P is. Right, and here's that, let's see, here's that formula for P of X that we talked about, that we kind of gave a derivation from, but it's going to become simple when we actually compute it. All of these things they're simple when you actually do them, and they're a little more complicated when you do the math. And connecting those makes you a superhero when it comes to Bayesian machine learning. Okay, so here's question 1. Suppose we have a coin, and the coin's either fair, P is 0.5, or it's unfair with P equals 0.1. So we only have 2 possibilities here. Maybe we're at a fake coin factory, and it makes coins that have a probability of heads of 0.1 as like a trick coin or something. And we find a coin, we don't know, is this one of the fake coins or is this a normal fair coin, right? Does that make sense? Just those 2 options. So we want to figure out what's the probability of those 2 coins after doing some experiments. And so we flip the coins 50 times and we get 21 heads. So I want to know which of these types of coins is head. Now, sometimes it helps to just think without digging into the math yet. 50 times 21 heads, that's 0.42 or 42% heads. So which is 0.42 closer? Is it closer to 0.5 or 0.1? Yeah, it's closer to 0.5, right? A couple of answers in the chat. Yeah. So without even doing some math, we think it's probably a fair coin. But if those are the only 2 possibilities, but the question is, like, how confident are we, right? That's where Bayes methods are going to get us. How confident are we? Okay, so here's the answer to that problem. And so we're going to take this formula for the probability mass function. It's the one we were looking at on the slides. And we're going to plug in the 2 possibilities, either N is 50 and P is 0.5, and really we just care about this 0.5 part. Or we're going to do the same thing with 0.1. But let's do this over on the right-hand side. This is Bayes' theorem using 21 heads, N equals 50, and P is 0.5. The N equals 50 doesn't really matter. We could stick it on either side of this vertical line here. We could think of it as a parameter or part of the data, or we could just assume it's like a fixed part of the universe, right? It doesn't really matter. And so just don't think too much about where that N equals 50, whether it should be with the theta or the X in this formula. It's fixed all the time. So okay, so think of this as 21 heads. So we want to know what's the probability that P is 0.5. So Bayes' theorem says, where's Bayes' theorem? Bayes' theorem says, here's the probability of my parameter given my data. So that's this piece here. Then on the top, I have the likelihood of the data given the parameter. So I'm thinking if that parameter were fixed, what would be the likelihood for getting that data? And that's how we write it this way. And then we have this P of theta, and so that's our prior. So this is the probability that the coin is fair before we do any test. Now, if I pick up a coin and I say, do you think it's a fair coin? Right, if I just happen to have one in my pocket, or I go to the store and I buy something, they give me change. Do you think that would be a fair coin? What do you think?
Probably.
So Austin says yes, yeah, probably, a couple of yeses. I think probably too, right? It might be if I flipped it 1 billion times, it would come out heads 0.5000001% of the time or something. It might be slightly off, biased based on weights or something. I don't know, but it'd be really close to a fair coin, right? So we could build that into this and say, I have this probability that it's fair is pretty high based on our intuition. Or if I do happen to be standing in a factory that makes fake coins, I might say it's a 50-50 chance that it's fair or not fair. So for the moment, we're going to assume we know nothing about whether it's fair or not fair. So that prior is going to be 0.5, right? So that's the key thing. These priors, sometimes we just make them up to reflect our belief coming into the system. If we wanted to have something more rigorous, we would get him, 1,000 coins and flip them a bunch of times, and we could build a prior from looking at the universe. But for the moment, let's just say, hey, we're going to take that as 0.5, and so that's our prior probability, right? So the prior is here. That's going to be equal to 0.5. This is going to be what we get when we just stick this formula in, and on the bottom, it's, remember, this is the sum over all possible values for theta, right? We have two different values for theta. Theta could be 0.1 or 0.5. So it's the same formula we have on the top of this fraction, but we have it down at the bottom. It appears once for each of the values of theta that we're working with. Okay, so let's go ahead and see how to compute this. It becomes simpler and simpler as we get more concrete. So we're going to import a binomial distribution from SciPy stats, which will give us this function. So what we have to do is we have to compute some likelihoods. So K and N and P are going to be 21 and 50 and 0.5, right? This line is just a convenient way to set 3 parameters in one line. And so which case does that correspond to? Is that the setup for the fair coin or the unfair coin? Yeah, fair coin, great. Because there's a 0.5. So P is 0.5. In this case, our data is fixed, so it's always going to be 21 and 50. We're going to do this all for P equals 0.5. We're going to do it again for P equals 0.1. Okay, so L1 is going to be our likelihood for case 1, which is the fair case. And we get L1 by taking the 3 parameters we have above, 21, 50, and 0.5, and putting them into the binomial probability mass function, which is just this formula here. Right? So all we do is we stick 21, 50, and 0.5 in there. We get our likelihood, and that likelihood is 0.059. It's this number right here. Print. Right, so that's the output here. And this is this F printing in Python. It's nice when you do a print statement, if you're going to go back and forth between text and numbers. If you put an F before your first quote, you can go running along and have some text. And when you want to put a number in, just put it in some curly braces and then some more text. So let's look at this, n equals whatever here. That gives us the n equals 50, right? So it'll take whatever your number is and string it along in the quote. So that's a good, a nice thing to use. It's pretty succinct. It makes, I think, this pretty readable. So what we're saying here is the likelihood of this, it's equal to, here we're writing it as in the probability mass function formula type of way, right? In either case, we're really thinking of The 0.5 is the variable, because that's the thing we're going to be switching. The data, the 21 and 50 are fixed. Okay, so you put them in this formula up here, right? That probability mass function, and you get 0.059. We compute the likelihood for the other case, which is the data is still the same, and the parameter is 0.1. That's P, and we get this formula. Okay, so which of these likelihoods is bigger? Fair or unfair? Yeah, terrific. The fair case, right? And in fact, I don't know, it's about 9 times bigger or so, judging by the exponent. This is times 10 to the negative 9th. This is times 10 to the negative 1. So maybe it's 8 times bigger, something, several orders of magnitude bigger. So now what we want to do is we want to put these two likelihoods into this formula up here. So this here, this is L1 times 0.5 over L1, or sorry, L2 times 0.5 plus L1 times 0.5, right? So those are the pieces that we're going to put into that. And does this work pretty good with it kind of zoomed in? Is that all right? Okay.
Yes, thank you.
So
Thank you.
it's pretty good that way? Okay, good. So here's L1 times 0.5, right? That's the likelihood times the prior. So we're going to call that numerator 1. So that's the top in the fair coin case. And then we have L2 times 0.5, that's numerator 2. That's the top of the fraction in Bayes' theorem for the fair, for the, what was 2? 2 is the unfair case. And then the denominator in Bayes' theorem, it's always going to be the same. It's the likelihood times the prior for one of these, and the likelihood times the prior for the others. So we compute these 3 pieces differently. Here's the numerator for the fair coin case. It's this, which if you look up above, that's exactly 1/2 of the likelihood, right? Because it's just the likelihood times 0.5. So here's the top of the Bayes' theorem fraction for the fair case. Here's the top of the Bayes' theorem fraction for the unfair case. The bottom, that denominator, that P of X is this, right? And just to iterate where that comes from, that's here. And so what you can see here is this denominator, you can say its only role is we're going to rescale these two numerators so that they add up to 1, and the denominator is what does that. There's a reason I'll say the only role of the denominator is to make those add up to 1. So now, with those 3 pieces, we can compute the probability. So the probability that the coin is fair, that's P of, this is our theta given X, our data. And so the probability that it's fair is 0.99, however many 9s we have here, and then so on. Probability that the coin is not fair with P equals 0.1 is this, right? So it's the probability for this parameter value given the same data, and that's the probability for that. So this answers our question. You all told me, hey, I think it's probably a fair coin because 42% is closer to 0.5 than it is to 0.1, but I'm not sure if you could quantify with any like specific degree of accuracy just how confident you are that it's fair. At this point, we should be very confident that it's fair, assuming that prior belief that fair coins and unfair coins are equally probable. Now, if we incorporated something that says, out of every 1,000,000 coins you find, most of them are fair, maybe 10 are unfair or something, right? Kind of to describe your belief that coins tend to be fair. What do you think that would do to these results? Well, how would that change these probabilities? Instead of this 50-50 or 0.5 priors, we built in our belief that most coins are fair. How would that change these probabilities? Yeah, the probability of fair. Mauricio says probably P of fair would increase, and it's even more likely to be fair, says Ben. Not fair would even be smaller. It says Austin. All of those are correct, right? So this would get closer to 1. This would get closer to 0, right? Okay, so now let's consider a different situation. Same data, but we're going to consider a different set of possibilities. Yes, Hallie.
If we were to build in that like probability of, or like that prevalence of fair coins probability, would that be in the prior?
Yep.
Is that where we would
So-
put that? Okay.
Yeah, so suppose I thought if I pick up a coin, it's 1,000 to 1 more likely to be, or out of every 1,000 coins I pick up, 999 are going to be fair and 1 of them are going to be unfair. L2. Yeah, okay, N1 is the fair one. So uh 0.9999.
I think you have to do the same in the denominator.
Yeah.
Oh, thank you. I was like, oh no, math is broken. I was like, this should have been, it's a good question that Hallie asked, and it should be so easy to fix. Yeah, okay, so now, right, so we have more 9s here, and this is e to the minus 11th instead of minus 8th. So the nice thing is it's really easy in the computation to just change little pieces and ask different questions.
So in that change, the parameter like theta went from being kind of like a class label to like a prevalence value, right?
So
'Cause
in both of these, theta is a variable that can take, you could think of it as a class label in both cases, whether I have 0.5 and 0.5 or 0.999 and 0.01. You think of it as a class label, you think of a probability that's corresponds to a specific class of types of coins. Prevalence meaning like how prevalent each of those classes is. Yeah, so we're incorporating that information. We're incorporating prevalence in it. So you could think of the prior as corresponding to prevalence, I think is the right way to say that. Yep. But yeah. Okay, so question 2, we're going to ask a different question. And this is a really interesting thing is sometimes your results are skewed by what you consider to be like the realm of all possible things, right? And that's a theme that's going to come up a lot. But in this case, we flipped the same data, flipped the coin 50 times. We got 21 heads. But now we're going to not just consider those 2 values for P. We're going to consider 100 different values of P, which are 0, 0.01, 0.02, on and so on up to P equals 1. So what I want to do, let's see what our question says. So assume all those are possible values of P, and we have a discrete distribution, and use this to approximate the PDF for continuous distribution for P. So there's really 2 steps to this question. One is assume still there's only finite values for P, and what's the probability of each of these different specific values, right? We're going to, assume, yeah, just assume these are possible values. But then we want to kind of take that one step further. If P is really continuous, can take on any value in a continuous spectrum between 0 and 1. So we're going to do that as a second step. Okay, so for the first part, we're going to do really the same thing we did above with 0.5 and 0.1, but we're going to do it with 100 different values. So code starts the same way. We import a binomial function. This X is going to give us an array of all possible values for P. So this NP is numpy, A range says give me a range going from 0 to 1 with a step size of 0.01, right? And then we're going to print this X equals, and that gives us this sequence right here. So you can see really specifically exactly what that X is. And then we want to compute the likelihoods for each of those values for X, right? Before here, X, we could have used P instead of X. But sometimes it's a little more confusing to use P, or sometimes a little more confusing to use X. I don't know. So we're going to use probability mass function. And I don't know why this is 2 and 50. It should be 21 successes, 50 heads. But now for P, when we put in here, we're going to put in all those different values of X. So this will do a nice job of vectorizing this computation. So it'll keep K fixed at 21, N fixed at 50, and it'll let X run over all possible values of X that are in this array up here. So instead of having to compute L1 and L2, we're now computing 100 different values of L all in one computation. And so you can come down here. Here's all of our different likelihoods from that computation. And we said 0.42, which is a little before half, is where it gets the biggest. So I'm not sure exactly where that is, but probably somewhere in here that looks maybe around here. Maybe it's that one, where this is where the likelihood reaches its maximum. Right. In fact, there's some methods that are called maximum likelihood methods, where you get to here and you say, oh, that's the most likely one. 399, 3, 4, 5, 6. Okay, I'm being overly picky. I should not care. But you pick whichever one's the maximum and say, okay, that's it, right? And be done and not worry about how confident you are, right? That's a non-Bayesian way to do it. That's maximum likelihood methods would be something you would have done in like a machine learning class. But we want to compute all these different, consider all these different possibilities and how they compare to each other, right? Okay, so that's printing all the different likelihoods. Now, for the prior, I'm going to assume the same prior probability for all of them. And I want these priors the prior probabilities, this probability for each of the possible values for P or for X, and they have to add up to 1 because it's a probability distribution. So what I do is I'm just going to make that a constant, and it's equal to 1 over L. So the denominator is going to be what I get when I take these 100 likelihoods, multiply each of them by this prior probability, which is a constant, which is 1 over 100, because they're all equally likely. And then I add that up. So this NP sum right here is I don't have it done with a sum. It's this sum right here. It's the likelihood for each value, for a value of theta times the probability for that theta, the prior for that theta, plus the likelihood for another value of theta times the prior for that other value of theta, and summing them all up. And okay, so that's going to give us our vector of all our denominators, right? And just to see what that is, that's, oh, sorry, the denominator is just a single variable. It's a constant, right? Because we're going to get a probability for each of these different values for P. But in the base formula, the bottom is fixed, right? It doesn't depend on P's. It just depends on X. So that's what our denominator is going to be. And now here's Bayes' theorem. It's a specific likelihood times the prior for the theta that goes with that likelihood, or for the P of the likelihood, divided by the denominator. But we vectorize it so that we're going to compute them all at once and then print them. So, for example, we could compute, just to see what these things are, if I wanted the likelihood of 0.42 as being my P, like that would be I think about the 42nd value of P that we're considering. I could do this and it would give me, here's the probability that 0.42 is the proper probability of getting a heads. If I want the probability for 50, I would put, that's the probability for getting a 50-50 coin, or probability that this coin is fair. But we're going to do all those at once with this one line. right? So before we just had two possible values, p is 0.1 and 0.5. Here we have 100 different values. We compute them all at once. And that gives us this. And so this here, this vector of length 100, this is the output from Bayes' theorem. This is what we call the posterior probability, or the posterior probability distribution. Posterior meaning after we've compared our data to any prior information, or it's called our just our probability distribution for P. Now, it's a list of numbers. When we think of a probability distribution, we often think of like a graph or something, right? When it was just two numbers, it made sense, right? Probably this or that. But we can think of this, the probability that P is 0 is 0. Probability that P is 0.01 is this. Probability that P is 0.02 is this, and so on. Nice way to do that is to just plot X, which is all the different values of P, together with capital P, which is our posterior probability distribution. Remember, that's P, capital P equals this vector. That's the output from Bayes' theorem. And so it gets us this. And you notice the peak is at 0.42. So the prior, question from Jade, the prior is equivalent to the probability. So first I'll read the question. Is the prior equivalent to the probability of getting heads or the probability of fairness? So the prior is the probability of a specific value for P. So if we're thinking about the prior for P equals 0.05, that's the probability that the coin's fair. We're thinking about the prior for 0.42, that's the probability that it's fair with getting 42% of the time getting unfair, and gets heads 42% of the time. In this case, all our priors are equal to each other, but we could build in something that varies. Okay, so we can see with 50 flips, here's the probability is about a 0.42, right? That's about the maximum probability estimate. It's often called the MAP, maximum a posteriori probability, meaning maximum probability after we've done our work is 0.42. What do you think? So I could look at this and I could say, hey, it's reasonable, it's 0.42, but really anywhere from 0.2 to 0.6 is reasonable. Maybe 0.2 to 0.7 is reasonable, is half as probable as the maximum probability. There's different ways to quantify what you mean by reasonable. So I think it's 0.42, but I'm not real confident about that. I think it's probably not 0.1, right? That's a pretty low probability compared to the other probabilities. What if I, instead of flipping, let me see if you can guess what happened here. Instead of flipping this coin 50 times and getting 21 heads, what if I flipped it 500 times and got 210 heads? Can you describe to me what you think is going to happen to this graph? Yeah, exactly. Terrific. It's going to get narrower, right? We're going to get the same estimate as the most probable value, but we're going to be able to be more confident because we have a larger data set, right? Typically, if you want to be more confident, you get more data, right? That's a really common thing. So compute that, and then we'll compute the plot. And you can see now we can be really confident that it's 0.42. One of the important questions, and what you're going to do for homework, number one, is how many samples do you need, or how many times you need to flip your coin to get your confidence down to within some bound. Okay. Oh, Tom, you're a step ahead of us. So Tom says, question in the chat, why does total probability equals NP sum prior likelihood times dx on page 31 of the textbook have the dx, right? So right here, what we've done is we've computed the probability mass function. So we're going to get to that dx in a second. This is the continuous case. But what if we want to be a little more like realistic and say, hey, P is a continuous number, right? It doesn't have to be 0.51. It could be 0.510367, right? It's really we really should be dealing with continuous probability distributions for P, which is a little interesting because K and N are fixed and they're integers, right? So they're just, if we're thinking about them, they're discrete, but P is, we have a continuous probability distribution for P. So how do we modify this to turn it into something that sums, it's not going to sum to one. And I'll kind of give you the answer and then we'll walk through it. So I jumped back to the slides. I have the code that we just walked through on the left-hand side, the plot on the right-hand side. Excuse me. Here's our formula. And on the bottom of Bayes' theorem, we have this piece which makes the sum of these heights to one, right? If you add up the heights to all these dots, you get one. If you look at these, it's like the height here is about 0.06. So, right, so it's about 0.06. So if you added up the heights of all of these, they're going to add up to one. That's what it means to be a discrete probability distribution. What do we have to change to make it a continuous probability distribution, right? If we think about this as now being a curve, what does that curve have to satisfy? Yep, Hallie says we're going to have to do a Riemann sum, and that's, is it Hallie or Haley?
Hallie, like Halle Berry.
Hallie, okay, awesome, good. That's what yep, good. And okay, so we want to make do a Riemann sum that's going to add to one, or we want the area under the curve to add to one, right? Since we're doing things with computers, we use a Riemann sum to approximate the area under the curve. So before we had a sum over all possible values of theta, and now that's going to be an integral, which we approximate by a Riemann sum. So what we want is the integral of the really dealing with this piece in the bottom for the moment. We want the integral to equal 1. So when we compute this piece in the bottom, the denominator, instead of forcing it to be the sum of all these things, it's going to be the integral of all these things. We approximate it by this piece here. So just as before, there's the probability mass function, which is the same as before, the likelihood exactly the same as before, but now we have this dp, which turns into a delta I in the Riemann sum. And the Riemann sum is, we're going to approximate this by rectangles, right? That's what a Riemann sum is. We approximate the area under the curve by these rectangles, which are kind of sloppy with my pen, but whatever. And so this is the formula for the area of the ith rectangle, right? The height of the rectangle is this piece, and the width of that rectangle is this piece. So we're going to really do the same computation we did before. All we're going to do when we come over here is, when we want the sum of the likelihood times the prior, right? Before it was the sum of the likelihood times the prior. The only thing we're going to do is add this piece right here, which is going to be like the delta I, and that'll make the denominator, make everything integrate to 1 instead of summing to 1. Okay, so keep going back to here. So what we've done is we've added this delta theta, which is that delta I, and it's 0.01 because we have 100 rectangles and they cover a span of 1, so it's 1 over 100. That's the width of each of the rectangles, or the distance between values for p that we're considering. Our denominator is this. Bayes' theorem is exactly the same. The only difference is now our denominator has this one piece in it. Bayes' theorem is exactly the same. And then here's our output. And when we plot it with a continuous curve to emphasize that this is a continuous function, right? The only thing I did is I did a line plot here for the plot. And up above, I did a scatter plot. So scatter plot gives us dots, line plot gives us a curve. Yeah, to emphasize that it's a continuous thing here. And so now we could say, what's the probability that that p is between 0.4 and 0.6? And so we would take the integral of that area between 0.4 and 0.6, or sum up all the values that we considered where p is from 0.4 to 0.6. Okay, so here's a challenge question, which I think we might think about next time. So everything we had before was Bayes' theorem with a one-dimensional distribution. So we just had p as our parameter. So suppose that we have a single observation, P x equals 4.2. So our data now is just one variable, but theta, our parameter, has a mu and a sigma. So theta is now two-dimensional. So we could do all the same formulas we had above and figure out how do we get a probability distribution on mu and theta together, given this one value for x, right? And let's see if we have a plot where that gets to. Yeah. So maybe from this picture, so this is mu is on the horizontal side, x is on the vertical side. What seems to be the most probable value of mu and x, given that we took one observation from a normal distribution and got 0.42? Yeah, question in chat about office hours. Yeah, 1 o'clock this Friday. So I don't have anything going on, and I'm not going to get myself bogged down trying to fix quizzes. So 1 o'clock on Friday for office hours. Yeah. So if you look here, 0.42 was our one observation, right? We found one x equals 0.42 is one observation. So the best guess would be the mean is 0.42. We only have one observation, so as far as Bayes' theorem is considered, we probably have no standard deviation to think about, right? If we had 10 observations and they were around here close to 0.42, we'd get some idea of how much spread there is, and that would give us a better sense here. Okay, so that's the challenge question, and a couple of different ways to plot that. Okay, let's talk a little bit about priors. And we'll kind of nudge on this, and then we'll save the rest of it for next time. So what we've done so far is the uninformative prior, right? And that's this situation that we've done. We have this 21 heads out of 50, and our prior probability was constant for all of these. But you told me, and I agree, that that coins are probably fair. And so this is what we call an expert knowledge prior, where we want to build in some information that it's really more likely that P, right, X is all our values for P, that P is somewhere in this range here, maybe 0.47 to 0.53, right? It's rare that I would think of a coin being far from that. So I'm going to build a prior. So this is my prior probability distribution, and for P. And so I'm going to say the most probable value for P in my prior is 0.5, and the standard deviation is 0.03. So that's equivalent to saying I'm 95% confident that the value for P is between 5 plus 2 standard deviations, so that's 0.56, and 5 minus 2 standard deviations, which is 0.44. Right, so I'm 95. Given no data, before I start flipping the coin, I'm 95% sure my coin has a P in here, and so this plot is the prior, right? So that's my prior probability distribution for P before I do any data. Now we're going to compute the posterior probability distribution, which is when we combine the prior plus our data, the output from Bayes' theorem. All the same formulas as before. We take our expert prior. Where's our expert prior? It's right here. We computed the likelihood, so we have 100 likelihoods for all those different values of P. We computed those before. We have 100 values for this prior, which are the values that give us that plot. And then we're going to divide by the denominator D, which we computed above. And so now what we have is, and this is actually kind of where it gets fun. The blue is P if we have a flat prior or an uninformative prior, meaning everything's equally likely, right? 0.42 is the most probable value for getting a heads. But if I combine the fact that I've got 21 heads out of 50 together with the fact that I believe almost all coins are fair, then I get the orange, and I get this rigorous description for the orange of what the probability distribution is for what P should be for this coin I found. And What do you think if I go back to this switch where I have 500 and 210? What's gonna, okay, Hallie already told us what's gonna happen to the blue curve, right? It's gonna get skinnier and maybe taller. So if instead of flipping it 50 times, you got 21 heads, I flip it 500 times, you get 200 heads, 200 heads. What do you think is gonna happen to my orange curve? So what will the orange curve do? Let's go ahead and um, let's do a second case where we have more data. And it's going to be the same prior, but we're going to compute our likelihood and our denominator using more data. And coming up here to compute that, I'm going to make L2 here. X will be the same. D2 is going to be using L2 and 500 and 210. Right, so now I have a lot more data. Right, so now this is what happens to my probability density function for the constant prior. And down here, I want to compute this, and I'm going to add a third possibility, which will be the case where we have more data. So P flat prior, P expert prior, P expert prior with more data. Okay, I messed something up. All right, I messed something up because this shouldn't come up to 2,500. The area underneath that has to be 1. So I gotta go figure out what I did wrong. Gotta compute a denominator for okay, I'm gonna okay, well, what should happen, let me get rid of this. I think I tried to be too quick with a simple thing and I messed up my code. The probability distribution for the expert prior, when we get more data, it's going to come closer and closer to being the one when we have a flat prior. So as you increase your data becomes more important and your prior probabilities become less important. We're going to see that over and over as a theme. You always have a balance between what your data is telling you and what your prior belief is telling you. As you collect more data, the data part becomes more important. As you have a stronger prior, you're more confident about what you think about the world. That part will become more important. So there's always this competition between the two, and Bayes' theorem allows you to make really rigorous, accurate estimates based on how to put those two together. Okay, good. So that's the end of topics for today. And I guess I'm going to take a little peek at the homework. So if you go into the homework, so this is homework is, well, you can find it in the Canvas materials. This is homework number 1. I'm going to give you a little pointer to think about problem number 3. So this is problem number 3. I know we're a few minutes over, but I'm gonna give you a little help in the homework, and that'll be a nice thing. If you have to get to something like another class, you're free to go and then catch up on this little homework hint like later. But I'll kind of walk through it. So let's walk through the problem for homework problem 3. So what we have is a Gaussian distribution for observation. So we're taking data, and our data is from something that's modeled with a Gaussian distribution. And we have n data points. So you think we're picking flowers. We've picked capital N number of flowers, right? And the random distribution, normal distribution would model the height of a flower. So each xi is the height of a flower. And my distribution for these flowers, it has an unknown mean, right? So I don't know what the average flower height is, but it has a known variance, right? This variance of flower heights is 5, right? So I want to know, oh, okay, so here's our prior. So the prior for M, it's going to be a Gaussian with variance 10, right? So it's similar to, like, we had a prior for coin flips, had a mean of 0.5 and a standard deviation of 0.03. It kind of described what we believed before taking any data about coins. Here, we have a prior for the mean flower height, and that prior is going to be a Gaussian distribution. It has a variance of 10. It probably has a mean, but we don't care about it. So here's the question. The question is, how large of a random sample must be taken, i.e., what's the minimum value for n, to specify an interval having unit length 1, such that the probability m lies in this interval? So this, let's break this down into a couple of pieces, and this really fits with what we've been talking about. As you increase the amount of data you've collected, you decrease the kind of the spread on your posterior probability distribution, or you can be more confident in your final values. So this is saying, how big does n have to be so that our estimate on m, which is going to be normal distribution, has a small enough standard deviation that it's going to lie within an interval of length 1. So let's take those in a couple of pieces. So I have a probability distribution, and I want to be, let's just take this piece first. 0.95, so that's my confidence. I mean, 95% confident that my estimate for m is within this interval of length 1. So the center of my interval is at mu, and it has length 1. So where are my endpoints interval? So I have an interval of length 1 centered at mu. So where would the endpoints be?
Mu minus 0.5 and mu plus 0.5.
Yep, exactly. So we want to be 95% sure that the estimate for m, or that we're going to have a probability of 0.95 that m is in this interval from mu minus 0.5 to mu plus 0.5. And mu is the mean for a probability distribution. So how big does sigma have to be in this case, right? So I have a standard deviation. I want 95% of my data to be in here, right? It goes out to 0.5 in that direction, goes out to 0.5 in that direction. How big would sigma have to be so that my distribution has 95% of its probability in this interval? Right? Does anybody remember? And this is kind of a rule of thumb, like, if we have a distribution and we know sigma, we want 95% of the data within a certain distance of the mean. What's that kind of rule of thumb? Do you remember that rule of thumb?
$1.96.
Yeah, so if we take 2 sigma in this direction and go to mu plus 2 sigma and go down to mu minus 2 sigma, the amount of area that's within 2 sigma of the mean, right? The area under here is 0.96 or approximately 0.95, depending on how you round things. So we want 2 sigma. We can tell how big 2 sigma has to be from this. What does 2 sigma have to be?
So meaning like 2 sigma is just over 95%, right? Is that what you
Yeah,
mean?
2 sigma corresponds to 95%, but based on the question, we want 95% to be in this interval of length 1, which goes out 0.5 that way and 0.5 that way. So what number would we have for 2 sigma?
1.9 sigma equals 0.5 or about
Yeah,
2
yeah.
sigma. Yeah.
We could say 1.9 sigma equals 0.5, or if we're being a little rounding the way I am, which is fine also for here, we could say 2 sigma is 0.5, or sigma is 0.25, right? So this is like, I need to get enough data. The more data I collect, the smaller sigma is going to be, the more definite I can be about the value for M. And so now I know how far down I need to get sigma. I need to collect enough data to get sigma down to 0.25 or less. So if you go into Don Brown's videos, which will be in this module, we're given this piece of information that we have a likelihood with n trials of the so that's our n trials here, and we have an unknown mean, and this is a case where we don't know the mean, but we're trying to estimate capital N. But we know the variance, sigma, right? And we know the variance, which is 5. Then this is the probability density function, which we don't really need, but it, just for reference. Then there's some information on the prior. So our prior has a mean of mu naught and a variance of sigma naught. So something up above has to correspond to some of these variables. And I guess here, the prior for M is a Gaussian with variance 10. So this is going to correspond to something down in this box. I'll leave it to you to kind of think this through. And now we want to get the standard deviation less than 0.25. This formula tells us what, not standard deviation, but variance is going to be as a function of the number of samples, the mean for the variance on our prior, the known mean or variance for our data, and then here's that prior again. So by taking this n, making it big, we can shrink this and tighten our confidence interval until we satisfy that criteria. So I'll let you put those pieces together and think about it a little more. But what I kind of wanted to get you a little bit of framing the question and a little bit of where in the notes you should reference to look through the formulas to answer this question. So any questions on any of that today? Sorry, we went a little long. I know for anybody who's had to jump over to a class or should jump over, head right over. And then if you can watch the recording for this. But any more questions? The homework problems tend to be lengthy and require lots of thought. You tend to not get them the first time you look. You got to look, talk to somebody, come back and look, get some help. We'll talk about it together and come back. And so this homework problem is pretty typical in kind of that way. Okay, excellent. Have a terrific night. I'll do some office hours on Friday at 1 o'clock. Please take a look at the homework and post some questions, and I'll be walking through more of homework 1 in office hours. That'll be the goal. But excellent. Take care. Have a good night.
Thank you.
Hey, Dr. Basner, Basner, there we go.
Yeah.
Yeah, I'm interested in chatting about the prisoner's choice problem unless you're going to post solutions.
Sure. Yeah, I can chat about it. That'd be good.
Okay. Can I share a screen?
Yeah. Let me stop sharing my screen. And okay, I think you should be able to share yours now.
All right. Yeah. So I'll minimize this and this. And go to some probability review files. So a discussion of the prisoner's choice. And yeah, just comparing prisoner's choice problem, the Monty Hall problem. And the solution I liked the most was that for the Monty Hall, I came up with 3 hypotheses, which I guess were the 3 parameters. So a likelihood is the likelihood of the data given the parameter, or the data given the hypothesis in this case.
Yep.
So three hypotheses: cars behind door 1, door 2, door 3, and the probability of each of those is a third. And then I found likelihoods of the likelihood that Monty will open the second door, which is D. Data D is that Monty opened door B and found a goat. So that probability of that is a half. Likelihood of that Monty will open door B, given that the contestant chose door A, is 0 and the other one is 1. So this is all probably familiar to you, right?
So somewhat I have to always think it through again, because
Yeah.
there's like different ways to frame it. And then okay, so I like your prior probabilities. I like the kind of the rigorous way you're setting it up in the 3 cases. Yeah, and so theta corresponds to what door the car is behind, or in the same thing as theta corresponds to the hypothesis. So you have a prior for each hypothesis, or a prior for each value for theta. Okay, good. And then your likelihood is in case 1, so the data is we choose A, and Monty opens B and found a go. Okay, and I love the way you're framing it, because you're framing it very Bayesian way, right? That's your data, that you choose door A and Monty opened door B and found a go. So before we have any data, we think they're all equally likely. But now that we know that there's a goat behind B and that Monty opened B, so now the probability of getting this data, if H1 is true, meaning the car is behind A, is 0.5. So Yeah. Okay, perfect. Yeah, exactly.
Okay.
So I'm just thinking about how to justify when you have to consider the likelihoods of D given each hypothesis. So let me kind of talk those through. The first one, the likelihood of D given hypothesis 1 is 1/2 because hypothesis 1 means the car is behind A, and if the car is behind A, Monty could have picked either B or C, right? So there's two possible outcomes. So it's kind of like if we fix H1 as the truth, what's the probability that that we would get this data, that we get data D? So what's the probability that Monty would open door B and find a goat? It's 50-50 because he's got two options. He could open
Yeah.
D and get a B and get a goat, or C and get a goat. The probability if H2 is true, the probability of getting this data, meaning Monty opens door B and finds a goat, would be 0 because he would never open
Yeah, the door with the
that
car.
door. Yeah. And then for the third one, probability of D given H3 means if the car is behind door C and we've picked door A, he's only got one option. So he
Right.
has to open door B. Okay, great. Yep. Terrific.
Yeah. So ultimately, my question during this conversation will be about what are these likelihoods for the prisoner's choice problem? But we'll get
Okay.
there. So just going through Bayes formalism, I calculated the total or marginal probability, which is the sum for the three different parameters or the three different hypotheses of the probability of the data, that being Monty opened door B and found a goat, and the hypothesis is true. And then it was like breaking the sum out and then substituting in conditional probability stuff and then substituting in numbers and finding the total probability to be 1/2 for the Monty Hall problem.
Terrific. Perfect.
All right.
Yeah. And
Yeah.
that's
And
that
then
denominator. Yeah, good. Yeah.
then the probability of the car being behind door A, which the contestant chose, was 1/3. And the probability of door C having the car, given that I chose door A and Monty chose door B, found a goat there, is 2/3.
Yep.
And so that's why we switch.
Yep. Good.
Okay, so that's kind of the layout that I have, both for the Monty Hall problem and for what I thought was a good approach to the prisoner's choice problem. But I am interested in kind of working through the prisoner's choice problem with you a little bit.
Good. This is fantastic. Yeah.
So here's just the setup of the problem, and then I laid out the hypotheses as above. But in this case, instead of the car is behind this door, it's the given prisoner will be executed. And does this seem reasonable, this part?
Yeah. So your hypotheses are who's going to be executed. Yep. And
Okay.
then the priors are the same.
Yeah. And the data I called T for tell. I'm prisoner A, which is equivalent to me choosing door A, or similar anyway. And the jailer tells me, or prisoner A, that prisoner B will be set free, which is kind of similar to Monty choosing door B.
Yep.
Unfortunately, I have a little typo here, but let's just say, for the sake of this conversation, that this is 1/2. and as I have written here. So these are the three numbers that I want to work with. And you can tell me I'm wrong, but these are the three numbers I want to work with.
Okay.
So basically, I'm trying to reason in a Bayesian way about these likelihoods. And I guess that'll impact my ultimate answer. But do you agree with these likelihoods?
Let's see, the setup looks good. So let's talk through the likelihood. So this is a probability that the jailer is going to tell you that prisoner B is going to be set free under hypothesis 1, which is A will be executed. And if A is executed, we have a 50-50 chance that he would tell you B, right? He might tell you B, he might tell you C.
Mm-hmm.
And for H2, if B is going to be the one that's executed, that's hypothesis 2, the probability is going to tell you that prisoner B gets set free, given that B is going to be executed would be 0. And probability of telling you B is going to be set free under H3 hypothesis, which is C is going to get executed, is 50-50, because he might tell you B will be set free. He might tell you A is going to get set free. So that's the 3 is going to be 1/2, just like you said.
Okay, cool. Yeah, and I think after this conversation, I'll have to refresh, what my real deep thinking was with this.
Yeah.
So then I went again, but into calculating the total or marginal probability, and that was ultimately this times the prior of a third plus 0 here times the prior of a third plus 1/2 there times the prior of a third, which is in total a sixth plus a sixth, which is 1/3.
Okay, that makes sense.
And then
These are kind of
apply-
fun because I feel like it all makes sense, but I also have this feeling like if something's not done right, it might wind up with the wrong conclusion. But okay, good. Because I know these are these ones where connecting the math to the problem is sometimes a little tricky, right? That's kind of the whole. Okay, sorry, keep going. I agree with you. I agree with you. It's what I would do so far.
Okay. And then I just applied Bayes' theorem again, but instead of a half as the total prob, I have a third. And then the thirds cancel instead of the halves. So I'm left with the probability that prisoner A is executed given that prisoner A was told something is a half. And the probability that prisoner C is executed given that prisoner A was told something is also a half.
Oh goodness. So where did we go wrong? So it looks like we're coming to the conclusion that if he tells us information that it'll make the probability that prisoner A goes free become a half.
Yeah.
And we know that's not right. Because him telling us something or not telling us doesn't actually change any, like we don't have a decision to make based on it. Right? So him telling us or not telling us shouldn't change the probability. So we must have made a mistake somewhere in the setup, which I didn't catch. Okay, so can you scroll up to your setup part?
Sure.
You have these. Okay, I think what we're missing here. So there's really three possibilities of what the executioner might tell prisoner A. He might tell prisoner A that B is going to go free, or he might tell prisoner A that A is going to go free, or might tell prisoner A that C is going to go free. Now I'm kind of talking it out as they're thinking
Sure.
through as I talk now, and it's similar to before, where we had to consider the case where the goat, like we had to kind of consider all the different cases of where the goat might be. So there's something in here where we're not considering all the possible cases somehow.
Hmm.
Because what we're assuming is that prisoner B is going to get set free. But up above, we only know that the executioner is going to tell prisoner A somebody who's going to get set free, somebody's name. So if we knew that the name was going to be B, then it becomes a half, and that kind of makes sense. Because if we know B's getting set free and one person gets executed, it's now 50-50 that it's A. But the executioner might, or the jailer might tell prisoner A that, so we got to think about under H1, H2, and H3, three different hypotheses. What's the, what are the different things the jailer might tell her? And I think we could assume, what could we assume? Yeah, I think we probably have to consider all the possible cases. So we've got the three hypotheses, H1, H2, and H3. The jailer might tell prisoner A that prisoner A is going to go free, or he might tell him that prisoner B is going to go free, or he might tell him that prisoner C is going to go free. And I think for each of those pieces of data, we have to go through this.
So I need to calculate more likelihoods.
That's what my gut is saying. Because when we go to calculate the likelihood, we're assuming B is going free. But that doesn't have to be until we get to this tell line. The jailer could tell him that prisoner B is going to go through. He could tell him that prisoner A is going to go free. Or he could tell him that C is going to go free. And so it's something like, let's see if it works out, kind of thinking through my head, or I might wind up just messing it up. But the jailer telling him A or B or C are going to go through. Those are each equally likely, maybe. So it's a 1/3 and a 1/3 and a 1/3. If he tells him A is going to go 3, it's a 1/3 of the time. And A then has a 100% chance of going free. If he tells him A is free. If he tells him B is going to go free, then it's 1/3 times a half, which is 1/6. Yeah, I think somehow it comes down to thinking those through.
Okay.
And is the answer at the end here, when you add things up, 1/2?
Yeah, the probability of prisoner A being executed, given that, what's my language exactly? That prisoner A is told that prisoner B will be set free is a half.
Yeah. Yeah, okay, so scroll up a little bit to hypothesis 1, to the list of hypotheses. Yeah, it's gonna be something like if, so the likelihoods are if each of these things are true. So if H1 is true, then we go down to compute the these different likelihoods. So I think we have 9 likelihoods
Oh, wow.
because the jailer might tell prisoner A that B is going to go through, and you've got 3 likelihoods here for case B. And I think you have to multiply each of those by a third. And then you have to do the same thing with, if he tells him prisoner C is going to get 3, and you have to multiply each of those by a third.
Okay.
Because there's a 1/3 probability he's going to tell him C. And then if he tells A is going to go free, you have to multiply those by a third. I'm not sure that's exactly the right way to do it, but that's the right type of thinking. You have to like think of all possible cases here.
Okay. Yeah, I got some expansion of this problem to do.
Yeah.
Okay,
No, I
that
really
was-
like how you do it though, because you're doing it the right Bayes theorem way. Often people get here and are like, well, telling prisoner A that prisoner B is going to go free doesn't change anything because he can't make any decision based on it. So therefore it can't change his probability of being executed,
Mhm.
which is true, but there's no Bayesian reasoning to it.
Sure.
Right. So I really like that you're trying to do the full Bayes, compute the probabilities. But I think what you'll find out is yeah, kind of what you expect, that the probability that prisoner A goes free in the end is going to wind up being 1/3.
Okay. And so the ultimate goal is to find something like is this a problem where Bayes' theorem is applicable and ultimately a posterior probability will be a third? Is that my goal?
Yeah, I think that's true. And I think it's a problem where in the end, Bayes' theorem doesn't, it tells you that it's not telling you anything. That's sort of a roundabout way to say it, but it winds up like you pull it out with Bayes' theorem, you have all these pieces, but they just kind of wash out and get you back to where you started.
Interesting. So I will have a kind of a P equals P conclusion, or will
Something
I
like that. Like I expect what you have here is this probability of a half, and that corresponds to him telling the jailer telling prisoner A that prisoner B is going free. You're gonna have like 3 cases, and the probability of each of those 3 cases is 1/3 because they're all equally probable from the beginning.
Sure.
And that might split out by who the jailer tells prisoner A is going to be going free, something like that. But you wind up with a third times a half plus a third times a half plus 0 times a half, which in the end will give you your 1/3 that you started with.
Okay. Gotcha.
So here, so here you have like 3 of the probabilities, but I think there really should be 9 of them altogether.
And I need to bring some sort of like three times the conditional likelihoods. So I'm generating 3 times the likelihoods, and the contribution of each of those likelihoods to the posterior probability is a third of what it is presently, or something like that.
Something like that. And if you scroll up a little bit, let's see what I think you have this P of T given H1, and I think what you wind up need to be, you might have like 3 different types of T, like TA, TB, and TC. And then you'll have P of TA given H1, P of TB given H1. In the end, There's sort of
Interesting.
data in the sense that A learns about somebody going free, but that data doesn't really tell you anything that should change the probabilities. Yeah.
Okay, so then is this going to be like a double summation?
Yeah, I think so. I mean, that's what I'm guessing. That's what I would try.
Okay. Yeah, that'd be fun.
But that's really cool. No, yeah. I like it a lot. It's a good approach.
And just as a conclusion, like regarding this problem, in a sentence or two, oh, excuse me, why does the jailer telling prisoner A anything not influence that prisoner's probability of being executed?
Yeah, the jailer telling him anything, there's nothing that, like, his probabilities can be executed is 1/3 beforehand.
Yeah.
The jailer gives him information, but that doesn't change. Like A can't make any change based on what the jailer tells him.
Okay,
Right. So
that makes sense.
Yeah, there's something like if we're in condition H1, the jailer has a 50% probability that he'll go to TB as what he tells him, meaning tell him B goes through, and a 50% chance that we get a TC as what he tells him. I think you probably have to break it all down like that.
Sure.
Yeah, but I think assuming that he tells him prisoner B is going to go through, that means we're assuming TB as the data. Yeah. Does that make sense?
Yeah, that was very helpful. Thank you.
Yeah. Good. Yeah, good work. Thank you. You're very thoughtful. Good stuff.
Yeah. See you next week, I guess.
All right, good. I'll see you next week.
Bye.